welcome back to this topic on polymers, and we just like to continue on last class, which was second class. Now, we were discussing the classification of polymers, and we are talking about the classification of polymers based on mechanical behavior. As I have told you earlier that in some books you will find out that this classification is based on intermolecular forces in the polymer molecules, but probably this is a better classification, and we define stress and strain, and we basically discussed elastomers and fiber. If you recall, elastomer where the polymers where you basically have very weak intermolecular forces, and as a result you can elongate them quite easily, and the elastomers also have some little or slight cross linking in the chain. So, if I just draw a elastomeric cross linking network type polymer, so these are like slightly cross link network, and if you pull them, they will easily, because there is a very weak intermolecular forces between the polymer chain, they will elongate very easily, but because of presence of some cross linking, the later part it will be difficult for you to stretch further. So, that is why later part the modulus goes up, and so this is what elastomer is. And if I just talk about some of the properties of elastomer, once again it is basically low modulus, very high elongation. We are talking about elastomer. And this elongation what we talked about is reversible. That means, once you relieve the stress, the polymer will come back to the original position, and that is because of very weak intermolecular forces between the chains, and the chains are slightly cross linked. And examples we talked about earlier also is like Buna AS, and we will talk about neoprene later. This is one other example of this elastomeric product. In the second case we talked about was this case, which was fiber, which has high modulus, high tensile strength, elongation was low, and that happened because it has a very strong intermolecular forces between them, between the polymer molecules. So, in this case it was a very weak intermolecular forces, and in this case the polymer chains are the intermolecular attractive force between the chains are very high. As a result, they tend to crystallize, basically they tend to come together and crystallize and make a pack, so that it becomes difficult to deform them or elongate them. So, basically this is because of these properties of fibers are because of presence of strong intermolecular forces, and I will just write the example here itself. It is basically nylon 6/6 and maybe PET fiber. PET we talked about in last class. So, basically these are the examples of some of the fibers. Now, as I said that plastics would be somewhere in between, and plastics has a large variety. So, the third category would be plastics. So, it is a large variety of polymers which with wide range of mechanical properties. And they are between elastomers and fibers. So, the properties are in between, and we can have two types of plastics. One is a rigid plastics where the intermolecular forces are comparatively higher, strong, and examples. So, they will the intermolecular forces are comparatively higher. So, intermolecular forces are higher. So, as a result they will have high tensile strengths, high modulus rather, they have high modulus and they have very low elongation. Example could be a polystyrene, PMMA, which is polymethyl methacrylate, and the phenol formaldehyde resin. The other type of plastics would be flexible plastics, So, here the intermolecular forces are lower, comparatively lower, but higher than of course elastomers. Intermolecular forces are low. So, it will have comparatively low modulus, high elongation. Now, in this case the elongation what will have, these plastics will have, they are partially reversible. That means, if we relieve the stress, it will come back, it will not fully completely come back to the original dimension, but it will partially come back and partially it will not come back. And so, examples would be polyethylene, polypropylene, etc. Now, based on, so we basically have classified the polymers in terms of three categories based on their mechanical behavior under stress, which is elastomer, fibers and plastics. We can further classify the plastics into two categories, two subcategories where which is based on thermal behavior. One would be thermoplastics. In this case, basically these are linear or slightly branched polymers. They are capable of repeatedly softening on heating and hardening on cooling. So, you will have intermediate intermolecular forces. So, basically you heat the polymer, it will become like fluid and you can put it in the mold. So, it will take shapes of the mold where you have placed the polymer, and once it occupy the or get the shape of the mold, you can cool down and the shape will be frozen. So, that is how you actually melt this different shape of plastic material, and then it is basically you can remelt it. If you again heat it, it will become softened and you can actually again give shapes. So, these are the polymers are basically recyclable. So, you can basically if you the product is the work of the product is done. So, you can take it back and resoften and you can make a new product. Probably the properties will come down little bit, but you can do it. So, these are the recyclable plastics, and the second category is thermosetting polymers. So, these are cross-linked or very heavily branched, which undergo extensive cross-linking in the molds and become infusible. So, basically what does it mean that you in this case the polymers which have cross linkable groups. So, you basically heat it up and then the chemical reactions which creates the cross link between polymer chain, they will take place, and once the cross linking happens, when you cool down, this will occupy the shapes, but because the polymers are now heavily cross linked or highly cross linked, you cannot redo the same thing, you cannot re-soften and make a shape out of this polymer matrix again. So, basically these are non-recyclable is the not recyclable polymer materials basically. Examples could be bakelite, urea formaldehyde, which are cross link materials, and we have not given example earlier. So, basically polyethylenes, polyvinyl chloride, polystyrene, these are the examples of thermoplastics. As I said, in your book they may have basically classified these polymers based on their intermolecular forces into 4 categories, basically fibers, elastomers and thermoplastics and thermosetting polymers, but in true sense you can actually classify into 3 categories, fibers, elastomers and plastics, and then plastics can be basically of 2 types. So, it is a thermosetting plastic as a thermoplastics and thermo is basically you can further classify the polymers based on 2 thermal behaviors, one is thermoplastics, another is thermosetting polymers, and I gave you the examples here. Now, what will go you in the next case we just talk about little bit about polymer molecular weight of polymer, just very brief discussion. Now, in the first example, in the first class, what I gave example about, you people are in a class and in different benches, and imagine that you have the number of students in different benches were not equal. The class is not completely full. So, some benches will have 10 students, some benches will have 8 and some 9, some 11, something like that. And then I ask you to just join your hands. So, and once you make the polymers by doing just joining your hands. So, you will get different lengths of those polymers in the class. So, that is the case actually happen when you synthesize polymer. You get polymer of course of high molecular weight, but not all the polymer molecules in a mixture are of same molecular weight. So, you actually when you express polymer molecular weight, you express as a average molecular weight. So, when the polymer molecular weight is expressed as average molecular weight, and because it will have a distribution like this, where you have this is the say molecular weight of individual chain, and this is the number of polymer molecules. So, you will have a distribution like this and you have an average. Now, you can think that there could be a scenario where you will have same average, but maybe a narrower distribution of chains. So, probably in these two samples the polymer average, arithmetic mean of the molecular weights, they are same, but you can see that two samples are different. And normally we in statistics we basically get the standard deviations of two samples for comparing. So, in this case we basically, besides the arithmetic mean or arithmetic average, which gives us a number average molecular weight, number average arithmetic MW molecular weight, which is expressed as MW bar, number average molecular weight. We also to basically get or to express the distribution, we also express or define another average, which is called weight average MW molecular weight, which is written as MW this bar means average. And to find out the broadness, the broadness can be quantified with a ratio which is called PDI, polydispersity index, which basically quantifies, if this is high, then the broadness in the distribution is high, if this is low, then the broadness is low. We are not going, I am not giving you any expressions for this, you just know that Mn is just the arithmetic mean of the molecular weight present. So, basically total mass divided by total number of molecules present. So, that is basically the arithmetic mean. And this is probably is not in your syllabus, the expressions, just for your knowledge that polymers are generally polymer moleculars are always expressed as average molecular weight, and to express or to show the actual polymer distribution in a mixture, in a polymer sample, you cannot do it single molecular weight. So, you need more than one molecular weight, which basically will able to give you the distribution or the width of the distribution of the molecular weight in the sample. So, with this we basically complete the classification part, and we will now move to the next topic. We will move to the examples of different polymers, their preparation methods and some applications. Now, before I go into that, I just wanted to discuss few questions what we had read. These are the questions from your book, NCERT book. Just I copied from them, and then you can see I just want to discuss few questions. This is first question is explain the term polymers and monomer. Now, we discussed in the beginning the polymers are basically the macromolecules which are formed from many units which are covalently linked. The covalently linked is the catchword. So, when the many units are linked covalently to form macromolecules, large molecule we call polymer, and the units which are formed from one or more than one molecules, they are called monomers. Okay. We talked about natural and synthetic polymers. So, the natural polymers are those which are originated from plant or animals, and synthetic polymers which are synthesized in laboratory. And we have given many examples in last class. For example, natural polymers would be cellulose, protein, starch, and so on, and synthetic polymers, all the polymers we discussed afterwards, like polyethylene, polypropylene, the rubbers, those are basically synthetic polymers. The butane type synthetic rubbers, those are synthetic polymers. We talked about in detail what is a homopolymer and what is a copolymer. Homopolymers are when a polymer is formed from two different monomers, where individually the monomers are capable to form homopolymer themselves. Okay. If they are not able to, in case of say condensation polymers, we have found that this the polymers are formed from two different monomers containing two different functional groups, like say in case of polyester we have acid and alcohol, but that is not a copolymer. But if you have monomers with two different types of molecules having OH groups, then we call them as copolymer. I discussed in detail in last class. What is the functionality of a monomer? Functionality is basically the number of covalent bond one monomer can form. So, all the monomers like ethylene, propylene, styrene, they have containing double bond. So, they can form. So, if they have a double bond, this so they can form bond this way and this way. So, this functionality is 2. All the other monomers like the diacids, diacids or diol, they also can form covalent bonding from two sides. So, basically they also have functionality 2. In case sometimes you can have, so like I have a triol. OH. So, basically it can form polyester by reacting with carboxylic acid groups from these three sides. So, in this case the functionality F would be 3. So, in this case F is 2, F is 2, F is 2. So, in this case F would be our functionality would be 3. So, you know what is functionality of monomers now? The functionality of a monomer is the number of covalent bond each monomer can formed in that given condition. Polymerization is the process of converting monomers to polymers, and we talked about different types of polymerization process. Next question is this a homopolymer or copolymer? Of course, this is a homopolymer. It has been synthesized from one type of monomers. In which class the polymers are classified in molecular basis of the forces? Now, we discussed, I classified in terms of fibers, elastomer and plastics, but in your book it is written elastomer, fibers, thermoplastics and thermosetting polymers. So, you can choose whatever way you want to classify, but it does not matter as long as you know what are those term meaning. How can you differentiate between addition and condensation polymerization? Of course, you have to know the monomer and the polymer. If the polymers is formed just by adding the monomers one after one, then you have a addition polymers, and if the polymer is formed from the monomers and some small molecules like water or methanol goes out, then we have a condensation polymer. So, basically the polymers which are formed by addition reactions, they are called addition polymers, and the polymers which are formed by condensation reactions, they are called condensation polymers. Explain the term copolymerization and give examples. We have given, I do not want to discuss anymore, and write the free radical mechanism of polymerization of ethene. We discussed in last class, where we have basically 3 steps about initiation and then propagation and then termination. So, we discussed in last class. Few more question. Define thermoplastics and thermosetting polymers with 2 examples we just discussed now. Thermoplastics polymers are where basically when you heat the polymer, it will soften and you can give whatever shape you want, and you can cool. Once it cool, you can freeze the shape and you can recycle the material. Whereas, in case of thermosetting polymers, you basically once you heat, you make a uncross-linked polymer and then heat it. It will basically cross-link on heating, and once it cross-links, you cannot basically now recycle or infuse it again. Classify the following as addition condensation polymers. Terylene is nothing but PET fiber. I will just come back to the nomenclature, just I finish the questions. Terylene is PET, so it is a condensation polymers. Bakelite again we will probably discuss more one more after few minutes. So, it will be again condensation. Polyvinyl chloride and polyethylene are addition polymers. As you can see, they are just formed by adding the monomers one after one. Arrange the following polymers in increasing order of intermolecular forces. Now, in this case you have to identify what are these. You know, nylon 66 is a fiber, buna is a elastomer, and polyethylene is a plastics, thermoplastics. So, you know elastomer has the weakest among these 3 intermolecular forces. So, buna S would be the having least intermolecular forces, then the plastics, thermoplastics, and then the fiber which has the highest intermolecular forces. Similarly, in this case also this is 916 is again a fiber, neoprene is a elastomer and polyvinyl chloride is a plastic. So, this will have a least, this will have a highest and this will have in between intermolecular forces. So, basically if you get this type of question, you have to find out in which category they belong to, and once you know whether they belong to a plastics or a fiber or a elastomer category, then you can know what are the extent of intermolecular forces they have in between the chains. Write the next question, write the name and structure of one of the common initiators in the free radical polymerization. We discussed in last class like benzoyl peroxides, tertiary butyl peroxides or say AIBN, azobis, isobutyryl or nitrile. So, those are the commonly used initiator in radical polymerization. What does Bu and NaS stands for? BuNa-S polymers, S for styrene, Bu for butadiene, 1,3-butadiene, and Na is for sodium, because sodium is used to make the polymerization or have to bring the polymerization. So, now we will move to the next section, as I was discussing the examples of different polymers and their basically preparation methods and some applications. And in this case this will be little bit of information based. So, you have to remember some of the information with you, otherwise it will be difficult to answer in examinations. It's little more of a information based. So, I will first start with polyethylene. And it is commonly called is polythene. So, we call polythene bags and all these things, this is polyethylene. And there are two types of polyethylene, one is LDPE, low density polyethylene, sometimes it is written as LDP as well, and in this case this is formed radically. You take a ethylene molecule and basically apply high pressure about 1000 to 2000 atmosphere and high temperature 350 K to around 570 K, and you need some radical generator which you can get from trace of dioxygen or say peroxide, and you get a polyethylene. Now, it is basically because it is a radical polymerization. In one thing happen in radical polymerization is called chain transfer. Chain transfer is like if you like during the polymerization you probably have say one chain is already formed, it is already no radical is active. So, it is already there in the system, and another chain is say you are forming another chain with a radical at the end. Okay. Now, this has hydrogen, isn't it? This contain hydrogen. So, it can abstract one hydrogen, and as a result what will happen, this chain will get killed and you will generate one radical here plus one dead chain. Okay. This N hydrogen will come from here. So, this chain is now not progressing or propagating anymore, it is terminated, but you have now active center here, active radical. Now, you can get further polymerization here, the monomers can get added here and here. So, you can get branches from here, and as a result what you will get? You will get a polymer chains which long branched present in the sense. So, in this case what will result in will be polymers with long chain branching, and that happen due to chain transfer. And as if you have a branched molecules, when you mix them together they cannot basically pack very closely. If you have if you have a very linear molecules like this, you can pack one by one, but if you imagine if you have obviously flexible, if you are more flexible you cannot pack. The polymers, as I explained earlier, polymers are not like the sticks, they are more flexible. But even when you have in the flexible chains, even you have long branches, the packing becomes even more difficult. As a result, you get low density. I will write in the next page. So, because the packing is not high, low packing, you will get low density as a result for due to less dense packing, and they are flexible, their intermolecular forces are not too high. So, they are flexible and they are they can utility, their utility is their utility is over a long or wide range of temperature. They have good combination of strength, flexibility, impact resistance, and they are highly resistant to water even at high temperature. Electrical insulator and good solvent, chemical oxidation resistant. This makes this a very useful material, and their typical molecular weight is around, as I said, this the molecule, it is not very high molecular weight. Typical Mn would be around 20,000 to 100,000, and a PDI value would be 3 to 20. So, we talked about low density polyethylene. Now, we will talk about the second of the polyethylene is high density polyethylene, HDPE, high density polyethylene, sometimes is written at HDP, and this is done by addition polymerization of ethylene in presence of catalyst such as tetra aluminum tetraethyl aluminum, sorry, triethyl. titanium tetrachloride. And this catalyst combination is discovered by two scientists, Ziegler and Natta. So, that in response to their name, this catalyst is called Ziegler-Natta catalyst, and the reaction temperature is about 333 K to 343 K, and pressure is about 6 to 7 atmosphere. So, in this case you get linear, no branching, linear polymer. So, linear no branched polymer, and as they are linears, you can imagine they can pack very well, and as a result they have high density due to close packing. They are chemically inert, the packing is very good. So, they can resist lot of chemical, tough, more tougher and harder. The application could are plenty places, commonly like buckets. These are the common example which you will be able to know, buckets, dustbin, bottles, pipes. These are some of the examples you have. And this two scientists, Ziegler, full name is J-U-L-E-O Ziegler, sorry, this is Carl Ziegler. Ziegler is, this is Natta, is an Italian scientist, and he is a German scientist. They got Nobel Prize in chemistry in 1963 because of the discovery of this Ziegler-Natta catalyst, which enabled synthesis of high molecular weight linear high density polyethylene. Next, so we just talked about polyethylenes. We will talk about the second example would be polytetrafluoroethylene. Polytetrafluoroethylene, in commonly it is called Teflon, and it is synthesized as obviously like the polyethylene case and this this is tetrafluoroethylene, tetrafluoroethylene. So, basically this like polyethylene case, this is a addition polymers or chain growth polymerization, by which you get. So, this is a addition polymers, and the polymerization mechanism is a chain growth mechanism, and this is very useful polymer which commonly called Teflon, and the non-stick containers will have a coating of polytetrafluoroethylene Teflon on it, and it is a corrosive resistance. So, basically it is resistance to corrosive chemical reagents, chemically inert, it is also used as a lubricant. So, it is a low friction. So, it can use as a lubricant as well, lubricants, and also it used in making oil seals and gaskets. This is very important polymers. All the non-stick utensils we use, they are basically have a coating of polytetrafluoroethylene or Teflon, and because it is chemically inert and resistance to corrosive agent, they can be used in as a oil sealant and gaskets. This is we are talking about addition polymers. Now, the third example we will give is acrylonitrile. So, this monomer in this case is acrylonitrile. Polymerization from so you can use peroxide catalyst and so polyacrylonitrile we can sometimes write as a PAN. They use for is used for as a substituent for wool in making commercial fiber as Orlon or acrylic. Now, the applications of polyacrylonitrile is limited. Generally, it is combined with styrene and we synthesize, generally it is synthesized as styrene acrylonitrile copolymer. So, most of the used of acrylonitrile are as a styrene acrylonitrile copolymer, which are also called SAN, styrene acrylonitrile copolymers. So, these are the examples of some important polymers which are synthesized by chain growth polymerization, or this is examples of addition polymers. Now, we will talk about some of the polymers which are condensation polymers, and they are synthesized by step growth mechanism. So, we will give now example of condensation polymers, and they are synthesized by step growth mechanism. As I said, do not just use these two synonymously, just like addition and chain growth, because in most cases as I told in the last class that these are most cases condensation polymers are synthesized by a step growth mechanisms, but there are exceptions. So, these are not synonymous, cannot be synonymously used, but they can be used together in most cases. So, first example would be in this case would be polyamides. Now, as the name suggests, you know, this is in the polymer backbone you will have amide linkages. So, in the backbone you will have amide linkages. So, we will have polyamides which contains the amide linkage in the backbone. So, you can get direct you can synthesize by direct, you take a diacid plus diamine and make a direct amidation reaction between these two to form polyamides. If you have cyclic amides like lactams, you can ring open. So, we can make direct amidation, we can do amidation to synthesize polyamides. You can take cyclic amides like lactams and then do a ring opening polymerization, So, basically open the ring and it will form one of the most important polymer in this polyamides region is nylon 6,6. So, basically you take two monomers, one is hexamethylene diamine. So, NH2CH6. So, this is hexamethylene diamine plus adipic acid, which is and you can make direct amidation and you will get the structure of the polymers we have drawn yesterday as well, but I will draw one more time. So, this is the repeat unit of the polymer and then water will come out. You have N here. So, this is the amide linkages and the actual name of this polymer is hexamethylene adipamide. Okay. Hexamethylene adipamide, but is very commonly known as nylon 6,6, and in case of nylons are a class of polymers where it is a polyamides, class of polyamides which are synthesized from a diamine and diacids, and the first number when you write nylon 6,6 or we can write there are many ways people write nylon 6/6 and somebody writes nylon 6 something like that, they all are same. And basically this first number corresponds to the number of carbon atoms in diamine and the second number corresponds to the number of carbon atoms in dicarboxylic acid. Okay. So, if you had say you have 2 and 6, which means it will be a 2 carbon here and 6 carbon here, the same monomer. So, accordingly we will name nylon. Now, as an example that you can be synthesized by a ring opening polymerization, you can take a caprolactam, which is a 7 membered one, 2, 3, 4, 5, 6, it's not, it will be 7 membered. So, this is 7 member cyclic amides which you can ring open in presence of some catalyst and you can make so this is nylon 6. this is this does not grow, the polymerization does not happen in a chain step growth mechanism. It is more of a addition or more of a chain growth mechanism in this case. So, this is another example where it's type of addition polymers which are not condensation polymers, which are though it is not a condensation reaction also, but looking at the polymers you will think that it is a condensation polymer. So, you will you cannot say that this is a step growth or chain growth polymers just looking at the polymers. The examples the use of nylons are in many cases nylon 6,6, there are many uses like hosiery, textile, stretch fabrics, sheets, etc. and nylon 6 would be like tire reinforcement, ropes, fabric and so on. So, we talked about one example of condensation polymers, which polyamides, and next class we will talk about the other condensation polymers like polyesters. And so, we will stop for this class now, and we will just continue discussing the synthesis and use of several common polymers, and we just talked about the important addition polymers like polyethylene, polyacrylonitrile, and one more we talked about. And in case of condensation polymers, we just talked about polyamides, and we will talk about the others important polymers like polyesters in the next class.